it's actually 4. I can introduce our speaker. So it's my great pleasure to introduce Egor Kiselev here to give our condensed matter seminar. Right, as I mentioned earlier, we had the pleasure of Philip Moll, another person at a different, well, I learned recently there are multiple Max Planck institutions, different ones. So Igor's currently a postdoc at Max Planck in Dresden for the Institute of Complex Systems. He did his PhD at Karlsruhe Institute of Technology with Jörg Schmalian, I believe.
That's true, yeah.
And then went on to where he currently is now. So I met Egor actually through indirectly through Brown. Brad Marston ran a Boulder summer school in hydrodynamics. I believe it's 2022. A few years ago, when I was a postdoc, and we met there. We were one of the few, I guess, how do you say, like quantum, hard condensed matter theorists there, because it's like hydrodynamics across all scales, and we were one of the few people there talking about electron hydrodynamics and hydrodynamics and quantum matter. But Egor has done a lot of different things outside of that as well, and so a lot of good transport work. So here he's going to tell us a little bit today about some new things on phonons and how I guess nonlinear phonons can do something interesting in materials.
Yeah.
The floor is yours.
Yeah, thanks a lot. And thanks for inviting me. It has been a very nice visit. Actually, I enjoy the weather. It's true. I like to see the snow, and it was nice. Also, it's sunny today. So, yeah, I'm going to speak about dynamical breaking of inversion symmetry with nonlinear phonons and associated with it non-equilibrium ferroelectricity caused by these phonons. And so from the mathematical point of view, what I will be talking about will be nonlinear dynamics, physics of driven nonlinear oscillators, and instabilities in these oscillators. And this is something that has to do with parametric resonances. So I want to start with a very short introduction to parametric resonances. So parametric resonances are basically the operating principle behind swinging on a swing. What you do is you can extend your feet and contract them back, and by that you change the center of mass of the swing. And if you do this with the resonance frequency of the swing, you can supply some energy to the swing and excite oscillations. And a very simple model for that would be a particle on square potential. So the way you can model it is the particle goes back and forth, and when it's on the outer edge of the trajectory, you increase the resonance frequency a little bit. That means you stiffen the potential, and by that you are able to supply a little bit of energy to the particle. Then when it goes back, you relax the potential again, but the particle's at the center, so it does not really notice anything. And then doing this time by time after time, you can supply more and more energy to the particle and excite oscillations in this way. It's a very simple idea, actually, but from this, say, toy model, you can already extract a lot of useful information. First of all, there will be some phase locking. That means that you have to do this operation of stiffening the potential at the right time. You have to do it when the particle is at the outer edge of its trajectory. For example, if you release the potential here, then you will subtract some energy from the particle. And if you do a simulation of such an oscillator, you will see that it's very nicely phase locked. So the other thing that you can see is when the resonance happens. So these operations, you can either do it each time the particle is here or here. That would be twice per cycle. So this would be modulating the resonance frequency is a frequency that is twice the resonance frequency, because it's here and here. That's one period, and then it repeats. You can also do it just each time it's here, or you can do it every second time, and so on. And these are the different conditions for parametric resonance. You have to do this operation of stiffening or changing the resonance frequency at a frequency that is 2 times your resonance frequency divided by an integer n. And for n equals 1, you are doing it each time. Of course, when n increases, you are supplying less and less energy because you are doing this operation more and more less and less frequently. And a third thing that you can see is that the amplitude will actually grow exponentially. That is because the more energy you supply to the particle, the further the particle travels on this potential outwards, and then this operation of stiffening and releasing gives you higher increases in energy for the particle. So it's like a self-amplifying mechanism, and it triggers exponential growth. And this is actually how many instabilities in driven nonlinear systems are initiated via parametric resonance. So you have some solution, but then when you have a small perturbation to this solution in the unstable regime, this perturbation via this mechanism starts to grow exponentially and brings you eventually to another state. And what I will be talking about is in principle an example of such an instability. So physically, I will be talking about nonlinear phonons, and they rose to fame with some papers that claimed that driving phonons can help to increase the TC of superconductors. So there were quite a few publications on that and some theories that try to explain that in terms of driving of nonlinear phonons. Of course, we know that phonons have to do something superconducting pairing. So that was the main idea behind how this increase of TC works. But there has been also a number of papers since that are thinking about how to use drive phonons in a way so to change phases of condensed matter systems, for example, magnetic order, or simply creating effective magnetic fields in the unit cells by phonons that trigger ions that go in circles, and then these, of course, will couple to the electrons and change the dynamic of electrons. So there are many ways that phonons can change, driven phonons can change the behavior of electrons and condensed matter systems. And so it triggered an amount of work, and one particularly interesting work for what I'm going to talk about is this work by Van Hogen from 2018, where actually they used harmonic generation from a sample of lithium niobium oxide to map the potential in which a phonon is oscillating. Basically, what is oscillating here is, I think, an oxygen atom, and this is the oscillation potential. And in fact, this is a quite highly nonlinear potential. So if you kind of write down a very generic formula for this potential, you can determine the coefficients by looking at the harmonics that are generated when you shine light on this potential. And because this material does not have an inversion symmetry, at least this mode, this potential will have all kinds of interesting terms. For example, it will have a cubic term, which obviously is asymmetric, term that causes the phonon displacement to the power of 5, which also is asymmetric. And this is actually quite close to the phonons that I will be talking about, but I will be talking about a little bit different case in terms of symmetry. I will be talking about also such a nonlinear potential, but in this potential, I do not want to have any inversion symmetry breaking kind of put in by hand or built in by nature. I want to have a inversion symmetry preserving potential where you only have a quadratic term, that is of course just your harmonic oscillator, and the term that goes as q to the power of 4. This is a nonlinearity, but it is a symmetric nonlinearity that preserves inversion symmetry. And what I want to do is, I want to show that you can drive such a phonon in a very specific way, such that this inversion symmetry that you have when you don't have these terms is broken dynamically, is broken via a nonlinear instability of your system. And what you get as a result of this symmetry breaking are signatures that are known to emerge in materials which do not have an inversion symmetry. And this is second harmonic generation and also DC response or DC rectification of your driving signal. So both second harmonic generation and DC response are quite interesting. Actually, second harmonic generation is used as a symmetry probe. For example, here I have a paper where second harmonic generation was used to detect a charge density wave that breaks mirror symmetries. And here we have the material, the second harmonic generation, above and below TC. So here the mirror symmetry is broken, and you see that it changes quite a lot, the second harmonic profile, because once this mirror symmetry is broken, it gives additional mechanisms for creating second harmonics. And DC response, the other signature is also quite interesting, because here we are speaking about phonon modes which are infrared active. That means they have dipoles to which an electric field can couple. This also means that if you squeeze such a phonon mode, it will create an electric dipole. And this is more or less how ferroelectricity works. So this is the example for ferroelectricity in this material as an what is tin telluride. So you have a very simple lattice structure here, and then one of the phonon modes actually below a given temperature develops an instability, and in the ferroelectric phase, inversion symmetry is broken, and you have dipoles because the atoms are squeezed a little bit. And so you create dipoles, and you can measure a dipolar response of the whole crystal. So in our case, this will be also a DC response in the sense that it is a drift of the atoms from their equilibrium positions, but this will be due to driving. And again, if your system would break inversion symmetry, this is something you would expect. But for a system that does not break inversion symmetry, this is actually unexpected, and you'd have to do something special to get it. And what you have to do, that will be basically the remainder of the talk. Right, so the system actually that I want to study is very simple. So I showed you on one of the first slides the potential that has a quadratic and power to the 4 term, quartic term, that was the word I was looking for, quartic term. Then in terms of equations of motion, you just have a harmonic oscillator coming from the quadratic term, and then from the quartic term you have q to the power of 3, a cubic non-linearity, and then you drive it with an electric field. And then it's actually quite easy to see that having second harmonics and DC response is actually not that easy, because, okay, you start driving it, say you're driving it with a small amplitude, then you will just get a response at the frequencies which you're driving because the system is nearly linear. Then you start increasing it, then you might think, okay, let's do some kind of perturbative analysis. So this will couple via this nonlinear term to harmonics. And so you raise your cosine to the power of 3, but then you only get your cosine back, and you get at the third harmonic, something like cosine 3 omega t. You raise it, okay, then you take this as a perturbational ansatz, you put it again in your equation, you calculate the next order, and then you get harmonics 3, 5, 7, up to 9, but no odd modes. So this nonlinearity will never couple any even harmonics, like the second harmonic, to the drive. So from the perturbative perspective, it's actually very non-trivial to get something like that. And the same holds for DC response, because it's basically an even harmonic. It's a harmonic with frequency 0. Right. So thinking in terms of space, it's actually not so easy to see from this example how a second harmonic generation breaks inversion symmetry, but one can do something slightly different. One can go to this kind of phonons where the ions go in a circle, and a simple model for that would be just 2 normal phononic modes, one in qx and one in qy directions. And then you can drive them with circularly polarized light, and you kind of send the phonon on a circle by doing that. And then imagine it goes on a circle, but then one of the components suddenly gets a second harmonic component. That means that it wiggles twice, while on the other coordinate it wiggles only once. And then you get something like this. And that makes it actually very obvious how inversion symmetry is dynamically broken by second harmonic generation. You get a Lissajous figure, and well, this is obviously not inversion symmetric. So this is a very nice effect to illustrate this, and in fact, I will be talking about phonons that are as a fancy word for that, chiral phonons that they do this. They go in a circle where you can create such trajectories. Right, and then same holds for DC response. So as I said already, these are infrared active phonons. So whenever you have a deviation of your phonon mode from equilibrium, you create a dipole. And then if you have a DC offset, that means you have some displacement and some oscillations on top of it, but the displacement is static, so if you average over time, you get something like a ferroelectric state coming from this dipole and then oscillations on top of it. And actually, these examples are from a simulation of this very simple system of nonlinear equations. And you can kind of see that, in fact, the whole figure is a little bit shifted to the right, so there is definitely a DC component to it. So if you average over this figure, the center of mass will be not exactly the center. And this is this DC response that I'm speaking about, which will give you something like non-equilibrium ferroelectricity. All right, and actually there is an interesting story behind this, how I discovered the instability that I will be talking about in a couple of slides in more mathematical terms. But the way I saw it first was actually before my PhD, even when I worked in a group as an assistant, and I made some experiments on superconducting circuits, namely on squids, which is basically a ring of superconducting material, which has a Josephson junction here. And you can describe such squids with a nonlinear equation, quite similar to the one I showed you, except that the nonlinearity here is sine phi, and the phi is the magnetic flux going through this ring. So it's like a wire, which is, of course, an oscillator due to the inductivity, but with a built-in Josephson junction, which gives you this nonlinearity. And what I was studying there was I had a whole array of these squids, and I was sending two signals into this array of squids via this coplanar waveguide here. One signal was a very strong signal, which is the driving tone, that was used to establish some kind of non-equilibrium or driven state of the squids, and then I send in a very small spectroscopic signal which probed the response. And for example, what we were able to observe are blue shifts and all kinds of interesting things that the resonance frequency of the squid does when you increase the power of the driving tone. Well, this can all be explained by basically doing perturbational analysis of this equation. But one interesting thing that I saw were gaps in these resonance curves, and these gaps were located at kind of curious frequencies. For example, here I was driving my squids with a signal of 6 gigahertz, and then there was this gap around 12 gigahertz, which is twice the frequency. And so I got curious about this and did numerical simulations and saw that second harmonics are generated there, but I didn't know that it's something special back then. So when we wrote this up, actually one of the reviewers complained that you're writing that there are second harmonics, but there shouldn't be second harmonics there because your system is inversion-symmetric. Indeed, if you take this equation, send phi to minus phi, you will see that it's symmetric. So the system is inversion-symmetric. There shouldn't be any second harmonics. But nevertheless, I saw them. So I got some complaints, and then I was looking for literature that actually would explain this, and I found this kind of obscure paper from 1990 where people saw something similar in the Duffin equation. And back then, for me, that was enough. I just referenced it and wrote, look, there can be second harmonics, and it was enough for the time. So it was published then, but I kept thinking about it somehow. I thought that it's something interesting because there is symmetry breaking going on, and I was all the time trying to, well, not all the time, but whenever I saw some system, I was kind of thinking, well, can I do something similar with a system which would be maybe more interesting than superconducting structures? And then at some point I saw this phonons, and I thought I will go for it with the phonons. So now maybe let me get into the mathematics of how this works. So Okay, one can do it with this system for the chiral phonon, which goes in circle, but actually it's the easiest way is just to look at one component. So let's take the QX component and drive it, and I already explained why one wouldn't expect second harmonics here. But nevertheless, if you do simulations and know where to look, you can see the second harmonics. So I was trying to devise some kind of mathematical apparatus to see them emerging. And what I came up with is I take my component QX, which describes the phonon displacement, and I separate it formally into a term which contains all the odd harmonics and all the even harmonics. And what I mean by that is, well, this contains first harmonic, third harmonic, fifth harmonic, and so on. This contains all the other ones, second, zero, fourth, and so on. And then in terms of symmetries, they differ in what they do when you shift the time by half an oscillation period. Namely, the odd components, they change their sign, and the even components, they do not. So the linear response that you would expect would be just cosine omega t. So if you shift it by half of the period of the drive, it would certainly change its sign. Second harmonic would not change its sign, so it would be here. Okay, and then because these have different Fourier components, they are linearly independent. And what you can do is you can rewrite your equation as two equations which are coupled, and one of them will describe the odd response. Well, somewhat unsurprisingly, this will look exactly as the equation you first wrote down for the full mode. And this you can approximately solve by assuming that the response is mainly at the frequency at which you're driving with some phase difference. But then there will also be an equation for the even modes, and this will be more interesting. Because first of all, well, the drive is obviously odd, so it will not couple to this equation. So there is no drive in this equation, but from this q to the power of 3, there is a term that goes like q odd to the power of 2, which is even times q even. So it's something even times something even, and it's even. So and this is this term. So this is, if this is q odd, this is something like q odd squared. And what it does is it gives you this oscillating cosine here, and it also gives you a reshaping of the resonance frequency because it has something like a constant component. If you take cosine to the power of 2, it's something like 1 plus cosine to omega t divided by 2, I think. So the constant component gives you a red shift in this, sorry, a blue shift in this case of the resonance frequency, and the component which is twice the frequency gives you this term. And yeah, so this is the blue shift I was talking about. This is just, the resonance frequency used to be omega 0, but because of this, you can call it renormalization of the resonance frequency from this component, it gets a term that depends actually on the amplitude of the response to the driving signal and to change your effective resonance frequency. I will show a plot of that in a second. And the second term is what I spoke about on the first slide. So this is actually, this is your resonance frequency of your harmonic oscillator, obviously. Then this is something introducing a slight change of the resonance frequency, periodic change. This is like the stiffening of the potential I showed on the first slide. So this is a parametric oscillator. And now you can ask for, well, usually, so this equation is not driven, so except for the parametric resonance, there will be no generation of even response, but there is a parametric resonance. And as we saw on the first slide, there is a condition for that. That should happen when the effective resonance frequency is even to n times omega, the driving frequency, and there is no 2 here because I already wrote the 2 down in the cosine. But then, by assumption, these modes have to contain even harmonics at the driving frequency, so you cannot really have 2 times. Sorry, you cannot really have the driving frequency by itself, which would be the instability that you generate by stiffening the potential on both sides. This is excluded basically by our assumption that this contains even harmonics. So the one you can have is the next one is n equals 2. And then what that means is that you're exciting oscillations with 2 omega via the parametric resonance, and this is second harmonic generation. So this is the condition for parametric resonance here. And then you can do simulation, and you can see how this works. So you have this blue shift. So when you start, you have your resonance frequency, that's 1. Or it's given in units of omega 0. That's 1, but then you start driving it with your electric field, that in this case is at 0.6, somewhere here. Down here, you start driving, and this gives you a blue shift. So your effective resonance frequency due to this term that depends on the power or the amplitude with which you're driving, it starts to grow. And at some point, it hits 1.2, which is twice the drive that's here. And then, via this parametric instability, there will be a region where Q even will become unstable, driven by the parametric resonance here. And this is the region, you can calculate the region from the equation. This is the region between these two vertical lines. And this is where you get the second harmonic response. And then you see some second harmonic response, but then when you drive it too strongly, the resonance frequency blue shifts away from this resonance, and then you don't see anything. So actually, it's a kind of peculiar instability, because you have to tune two things for that. You have to tune your frequency, and you have to drive with the right power, because you have to adjust the blue shift to the resonance frequency. Okay, maybe I can even omit this. This is just saying that if you want to do it for this chiral kind of phonon, you have to drive it with elliptical light, because the circularly polarized light, the components will cancel out due to some unfortunate phases, but maybe that's not so important. So now the thing is that we saw the instability, and we saw that it can generate some second harmonic response. But the cool thing about it is that it will actually go to a steady state after the onset of the instability. So you have this instability where with the parametric resonance, your second harmonic component starts to grow exponentially. But then you have the non-linearities, and when your response is large enough, the non-linearities will trigger, will force the amplitudes of your harmonics to converge to a steady state. I don't have an analytical theory for the steady state yet, also I think it's something definitely that could be done, but numerically it's very easy to study, so you just integrate the equation of motion of your oscillator, and in this regime where you have the instability, and then you look at the spectrum, you see that the response does not change strongly over time, so it's a steady state, and you can look at the spectrum of the steady state. And it has, unsurprisingly, a strong second harmonic component, because this is what triggered the instability in the first place, and also a DC component, which is not quite as strong, but still substantial. And so physically, this means you get this kind of asymmetric trajectories if you consider the chiral mode that goes in circles, which is cute, but also interesting, because if you think about it, ions going on such a trajectory, they will generate pretty non-trivial magnetic fields in your unit cell. You can think of it idealized as two semicircles. So here it goes in a semicircle like that. Here it goes on a semicircle in the other direction. So it will create a magnetic field showing up here and showing down here. And having such a staggered magnetic field in your unit cell is definitely interesting, because it changes the symmetries of the unit cells, and the electrons will couple to it. So it would be interesting actually to study some more concrete example and see how this reshapes your band structure in the sense of flow K physics, flow K engineering. And then maybe the physically more immediate thing is the DC component, which gives you a dipolar response. So this basically is you shine light on you excite your phonons, and then what you get is a polarization of the whole crystal. So you get a dipole that you can really measure as an electric field.
So is there a critical
So this is a nonlinear effect. Is there a critical strength that you need to drive it before you trigger the instability?
Yes, this will be in a couple of slides, but of course, depends on your damping and the strength of your nonlinearity.
But somehow this, because you're looking at the Duffing equation, this is different from the normal route to chaos because chaos is normally frequency halving, right?
Yeah,
doubling frequency.
it's a bit yeah. Anyways, it's strange to look at slightly above half the resonance frequency. Why would you look there?
Right.
But that's where this lies. Yeah. So I think usually you would drive at resonance frequency, and you will see at some point above a threshold chaos.
Yes.
Okay, and this was basically the stage where I wrote the archive article about it and submitted it, and then I got reviews, which were actually very interesting because people, for example, told me, okay, this looks like a dipolar response, but is it really a ferroelectric? Because a ferroelectric has domain walls, for example. The dipoles, they are a little bit like spins, and in the ferromagnet, you can have parts of the ferromagnet where the spins show all up, and other parts where they show down, and they are separated by domain walls. So here it's not spins, but it's dipoles, but you can still have very similar structures. And another thing that you get is hysteresis. This is actually a hysteresis curve from the original publication where ferroelectricity was first published by Waleszek, I think in Minnesota, just measured. Yeah, so but definitely you get hysteresis. So when you have these dipoles, but when you apply a DC electric field and sweep it through positive and negative values, you get memory effects, very much like you get them in a ferromagnet when you sweep the magnetic field. And so I looked at that, and actually I got the same thing. It looks a bit different because it's a pinched hysteresis curve, as it is called. But what I did is I inserted a DC electric field in my equation, and I swept it through positive and negative values, and I get the same memory effects. And this is actually indicative of the thought that there should be something like a double Landau theory for this kind of steady state, because this is very much what produces you the hysteresis curve. So it's one of the next steps actually to do. And then the question that Aaron asked, the thresholds. So yes, you can, of course, you have a threshold. So your electric field with which you're driving has to overpower this damping gamma, and there is a criterion for that. So this criterion you can calculate, and you can also do numerics and see that it fits well, but you have to be above a given critical amplitude to trigger this oscillation. And then, of course, you want this critical amplitude to be realistic. So you try to estimate it, and in a frequency range of couple of terahertz, where many of these modes lie, you get a field strength, critical field strength with reasonable assumptions for, actually high, but reasonable assumptions for quality factors of these phonons. So 100 oscillations before it decays. This can happen. You get a critical field of the order of 10 to the power 7 volts per meter, which is high, but reachable, but only with pulse signals, and that is important. I will say something about that in a couple of slides. But you can reach such amplitudes. And then, well, I mentioned chiral phonons as the ones that go in a circle, but actually there is a lot of discussion now going on what to call chiral phonons. For example, some people say they should be non-degenerate. So if they go one way, they should have a different frequency from when they go the other way around. And actually there are such modes. And you can also study such systems and create some interesting trajectories that break inversion-symmetry. And here, because there's frequency splitting between going left and going right, you will trigger them at different driving strengths and so on. Some stuff that is to be explored, but this is more like an illustrative thing. What is important is that this requires relatively high fields, and such high fields right now you get in pulses. So it's important to see whether your idea survives not having a continuous drive, but just pulse drive. And actually it does, but there's a caveat to that. Namely, we have to have, well, here it's kind of important that you have a well-defined amplitude for your signal. So if you have a Gaussian pulse, of course, the amplitude of this pulse will have some central value, but then it will strongly decline in the ends of the pulse. So what you need is a flat top pulse that kind of preserves. It can be very short, just 6 cycles here, or 5 cycles, but it has to have a nearly constant amplitude. And with such pulses, you can indeed trigger. So this is just a simulation. So you have the pulse. You can see in this area where you have the pulse, you have, this is the second harmonic, this teeth that you see here. And also it's shifted with respect to 0, so it has some DC component. You get this while you're driving the pulse. And then after that, it just goes back to the near linearized solution and oscillates with the resonance frequency. But in this period, you have you can take a Fourier transform and you have a very nice second harmonic. It's washed out because now it's just a pulse and not an infinitely long driving. It's washed out, but nevertheless, it's a very clear signature. And also you get some DC response here. Okay, so that's good. It survives pulse driving, which is actually a very nice thing because it shows that it's experimentally feasible with the kinds of powers that you need for it. Another thing that you can look at is, does it survive noise? Because you will do these experiments at a given temperature, and even if you don't do it, if you try to do it at 0 temperature, you will get some quantum noise. So it's good to test whether this survives some noisy driving term here. So for that, you can use a Langevin equation, and you can relate via the fluctuation dissipation theorem the amplitude of your noise to a temperature. And you can study, so these are the ratios of second and first harmonic with respect to the driving frequency as a function of how strong this noise amplitude is, given normalized by the frequency of the coherent, sorry, by the amplitude of the coherent driving. And you see that there is a critical noise amplitude at which the state collapses. So you have something again like a transition here. Again, you get this strange plateau here, which is actually very reminiscent of the pinched hysteresis. I showed a couple of slides back, so I think this will be somehow related to it. But all in all, you get a collapse of your symmetry breaking state if the noise is strong enough, and you can estimate, given this value of driving, critical driving, how large temperatures these are, and they turn out to be pretty reasonable, 100 to 1000 Kelvin, which is good. It means it is experimentally feasible.
I mean, wouldn't your phase be pretty stable because it's some attractive limit cycle? Like,
yeah, I thought so too, but actually you can destroy it with noise.
Well, I mean, the noise will just send you to, somewhere else. If it gets strong enough, it sends you somewhere else. Obviously, the fluctuations get large, but
yeah, it sends you somewhere else, and in this somewhere else, actually, the responses are much weaker. Yeah. So I'm not sure where it sends you. It might send you to your original near linearized solution.
I mean, has somebody? Well, it's the Duffing equation. Has somebody done the fixed point analysis?
Oh, I'm sure
for this, and you just look at the.
Yeah, I'm sure. I'm sure people have studied the Duffing equation under noise. Yeah. Not sure though if they tried driving it at half the resonance frequency, because this is kind of weird regime, which I actually discovered by accident by measuring these squids.
But the second harmonic and the DC signal survive the limit of zero noise and zero damping?
Zero noise, I would say.
So if you go to zero on the horizontal axis.
Yeah, they do, but there is still some damping. It's just that I would say that DC. My way of looking at it. So definitely, if you just have the equation with no noise, just deterministic equation, with some damping, yeah, that's the right way. If you have no damping, that's problematic because then you never set it to a fixed point. But there's always damping. So. All right. I'm sure I'm not the first one to analyze the Duffing equation with a noise term. Yeah, but actually, this instability is kind of niche. I really only found this one paper, this Olsen and Olsen, where one Olsen is written with one S and the other one is 2S. Yeah, I didn't find much about this instability.
But yeah, I mean, normally I don't think of Duffing as a parametric oscillator.
Actually, you do think of Duffing as a parametric oscillator because, for example, this this usual thing that we have. Is there a way to write something? So usually we have this multi-stability. It's kind of a very famous thing for Duffing.
This like leading Gaussian curve.
Yeah, you increase the field strength in this direction, and here you get just a harmonic resonance curve. I'm drawing two things like here. So this is the frequency axis. This is the amplitude of the response. But now you increase the amplitude of the driving strength and you get something like this. It leans over kind of. At some point it does this. And then there is an unstable region here. I think, yeah, this is unstable. Yeah. This is stable. I have to make it not look like too terrible. I think it is like that. Yeah. So there is a hangover there, and the hangover is unstable. And now, if you, for example, start with initial conditions here, so this is a fixed point, but you can add a perturbation to this and derive an equation for how the perturbation evolves. This will be a parametric oscillator. Just
I see.
Yeah, it will say you that the system tries to exponentially escape into the past scale with either by going here or by going. In our case, in this case, it's similar, but it's not this resonance. It's somehow you're driving it somewhere here. It's still something happens to the resonance curve. All right. Yeah, actually, I'm almost done. So. I think it's a nice topic because it's everything is reasonably simple here. It's just the Duffing equation. But still, there is a lot of physical implications. And there is a lot of things to do. One thing would be derive an analytical theory for the steady state to really see why it's pinched hysteresis and to explain the noise dependence and so on. But I thought, let's first see if this triggers some interest. And if it does, I will invest more effort in it. So I wrote it up. Another thing is that there are these domain walls, and this has been pointed out by reviewers, of course. And to describe them, you kind of have to do a field theory. So now I have an optical phonon that has a resonance frequency, and I'm driving it have this resonance frequency, but then of course this optical phonon also has a dispersion, and to think about domain walls and spatial effects I have to think about the dispersion, so I have to go to finite Q and do some kind of field theory for this kind of instability. And this is definitely something that one could attempt. Another idea is to go to the quantum regime, maybe, not using nonlinear phonons like from the solid state, but more something like optomechanical systems, where it's also kind of a phonon. It's this mirror oscillating, and it is driven by the electromagnetic field. And this inevitably will also have some nonlinearities, and I think you can look for similar effects there, second harmonic generation. Just because it will be quantized, there might be something interesting happening there. For example, in parametric resonances, often the fluctuations of the modes are squeezed. That means if your Heisenberg dispersion is kind of usually circular, x, delta x and delta p occupy a circle in phase space, but in parametric resonance, if you drive a harmonic oscillator, this goes prolonged, will become prolonged to a kind of ellipse, and this is called squeezing. So you reduce the uncertainty in one direction, say for x, and you enlarge it in the other direction, say for p, and this is kind of fancy effects that is studied in quantum optics. So you could have maybe something like that associated with the second harmonic. So definitely also an interesting thing to study. And then, okay, another thing is, can you maybe use this inversion symmetry breaking to trigger some interesting phases in the condensed matter system you're looking at, maybe some electronic phases, because this breaks the inversion symmetry of your system, and this is a pretty strong symmetry breaking, so it could enable some new states, some new phases, or if you have phase competition, maybe it can help you for your system to favor the inversion symmetry breaking state in favor of some other state, and then you could control this by driving the phonon. So that's another idea. Or maybe something like a phase competition between anti-ferroelectric and ferroelectric, something like that. This would maybe favor the ferroelectric. And another thing is basically what I briefly said when I was talking about the Lissajous figure, that it creates kind of a very interesting trajectory of ions in your unit cells. So, and there is a thing called Floquet engineering, which actually you're thinking about, you drive electrons periodically, and this reshapes your band structure and opens gaps in the band structure and produce all kinds of effects, and you can try to do something with these phonons. And because the asymmetry breaking, this again could renormalize maybe your bands in a very interesting way. So this is also something that maybe I will explore. Okay, and so summing up, I was speaking about the dynamical breaking of inversion symmetry with nonlinear phonons. And the main thing is here that I get symmetry forbidden electromagnetic responses, forbidden by inversion symmetry, which I break, second harmonic generation rectification. And this whole thing has the potential to serve as on demand, as is now fashionable to say, ferroelectric. So that means, okay, you have a material, and then you shine light on it, and then you kind of trigger ferroelectricity, then you switch off the light, and it goes back to its original state, and you can switch on and switch off the ferroelectric characteristics of your material. So this is the promise, I would say, of this kind of physics. And yeah, I've been talking about a recent upload of mine. If you're interested, you are welcome to and invited to check it out. And that's it. Thank you.
So I guess we have a good amount of time for questions.
Yeah, so I was thinking about the original paradox you posed of this naive perturbation theory not showing you the even order harmonics, and you basically said, well, just assume they're there, and then look at what they would do, and sure enough, they're there. So that one doesn't know if that's all one's doing, that's all that's there. If, for example, you thought there was a 3/2 frequency,
you're right.
Would you know that? What is the signature that you should have looked for that at the beginning?
I know for sure that there are more responses at fractions of the harmonics, not just second harmonic. I saw them numerically, so you're right. But I don't have a systematic approach to that. It's something that one would have to think about. But then maybe not all of them have really interesting physical implications, like ferroelectricity. Also, I don't know. I have to think about it. But you're definitely right that there are more of them. For example, I saw something by accident at 5/3 of the resonance frequency. I don't know where it comes from. Yeah, and you're right that I'm assuming that there is this even response in a way. Actually, if it's the same as with equilibrium symmetry breaking, if there is no perturbation ever breaking the symmetry, no infinitesimally small component that is a D-series displacement or something, or second harmonic, this equation will stay zero forever. So in this sense, I'm putting it in there by hand, but I'm relying on that there's always some perturbation that will make this grow. Because if you start with initial conditions, Q even is equal to 0 and Q dot even is equal to 0, this will stay 0 for times.
Very nice talk. So here, since you, at the very beginning, looking at this equation, you didn't talk about the momentum. I assume that you're having light coming down to your sample surface vertically. Right? So I'm wondering if you tilt So you're going to put out light. Can you actually make this effect localized or appearing periodically in space?
You mean like triggering a phonon with a finite wave vector, something like that?
Exactly, because you need the phase matching condition not just in time but also in space, right? So once you have this finite k momentum, then
Yes.
something's going to be different.
Yes, something is going to be different. The thing is that, okay, usually I think of light not having much momentum. So it might be problematic to really trigger a phonon.
But you can tilt it, right? So that's easy.
Maybe you can do that. It gets a bit complicated because, yeah, I would have to think about it. Now you don't have just one frequency, you have a whole dispersion, right, for all the Qs. So I'm not sure what it means to drive at half. Maybe you can do it like that. You can have a phase matching condition. Then basically you select one Q.
Exactly.
Yeah, and then you can try to excite this Q at driving close to half the frequency corresponding to this Q. Yeah, I think something like that can be attempted. I would be careful, though, if the light have enough momentum to do that. Maybe in a cavity or something, one can do something.
Yeah, so that's my background actually. So we couple different optical modes by this Bertillon scattering, right? You have this acoustic mode inside, so actually phase matching like 3 modes or even more.
Mm-hmm.
So that kind of effects can be rather pronounced.
Okay, so yeah, definitely something interesting. Maybe also for the more quantum mechanical part that I was speaking of, because this happens in cavities, I think. So.
Can you say more about the magnetic response of the chiral phonons that you set up? So you talked about you have some kind of magnetic imbalance.
Yeah. So originally, I think that's kind of a thing. I saw many publications on that.
Yeah.
Yeah. So this is just indeed you have.
If you have one chiral phonon, it's just moving charge. You have magnetic.
Yeah, so you have a magnetic field. But then if it does some pattern, so let's say it does something like that, 8 or something, then it will, when it's traveling here, it will have a magnetic field in this direction. When it's coming here, it will have an opposite magnetic field, and it will switch between the two.
Uh-huh.
So it becomes, you can think of it again in terms of log K. So it's a periodic switching magnetic field that shows part-time in this direction, part-time in this direction. Whether this does something interesting, I don't know.
So is there a way that you can make, so your DC response gives you a ferroelectric response, but then is there a way that you can also give in the AC response, it's set up a magnetic field, and so you think of it having like a multi-ferroic?
I didn't understand that.
But you have both you could have both magnetic order and
some order coming from this magnetism field, like some spin ordering. Well,
not spin ordering. It's a orbital,
orbital,
like an ionic orbital that gives a magnetic order.
Maybe
so at
except
the same
that,
time you have magnetic.
Maybe except that it switches kind of. So
but it switches, yeah.
It switches. Maybe you can have. I don't know, just speculating here, but maybe you can have actually some kind of phononic instability that, for example, extends your Brillouin zone or shrinks maybe your Brillouin zone so that you need two unit cells. One maybe shows that, one like that, something like that maybe. I would say it probably does something interesting, but I don't know what. I have to think about it. But it's not so straightforward because it's switching. So.
Thanks for the talk. So in the beginning, you started with 2 species of phonons, 2 chiral phonons, and then the equations became just purely 1D. So is the physics really just a 1D physics? Or?
Yeah, the physics is essentially this instability, you get it in 1D. But then, okay, so the reason why I drew this. So first of all, I wasn't actually so much focused on the ferroelectricity. I was focused on the second harmonic. This is what I remembered from the scripts. So I was thinking about how can you make this look like inversion-symmetry breaking. That's why I started considering the 2 modes, because this gives you a way to visualize it. really breaks inversion symmetry. But it's enough to look at one mode.
And how would it look like in 1D?
Pretty much like this.
I see, so
You
it's
see
not-
this extra teeth, kind of? This is the second harmonic. And the DC component just shifting certain atoms in the unit cell closer to others and then just oscillating around that.
So earlier in your talk, I don't know, for some, maybe this is just my bias of what I've done in my work previously, but why does terahertz? It always seems to be terahertz.
There are multiple regions for that, reasons for that. I'm getting tired.
Yes.
These reasons are, first of all, many collective modes are in the terahertz range. For the plasmas,
Right.
very terahertzy, many antiferromagnetic magnons in systems where you have anisotropies have a gap that is in the terahertz range or sub-terahertz range. So a lot of these, like the scales are such that a lot of these collective modes happen to lie there. This is one reason. Second reason is for a long time people were speaking about the so-called terahertz gap because it was kind of difficult to create terahertz lasers, and then these two kind of came together. And these phonons, they are also often the terahertz range, but I would not. So probably there are also different frequency ranges that are accessible to this effect, but somehow the community focuses on that. Right?
Yeah.
Probably due to the reason that many collective modes lie in this frequency range.
So another question. So you mentioned that. Wait, am I? Yeah. So so I assume that the Duffing equation should have a third harmonic generation.
Duffing equation? Yeah. Yes.
So I wonder when this second harmonic hysteresis loop is produced. So what's happening to the third harmonic generation?
I don't know, but you can have a look at this chart. Yeah, you get a third harmonic. It's just smaller in amplitude.
How do you compare that when you are away from this region?
Didn't understand that. Compare it to whether it's stronger or smaller if you compare it to.
So, for example, if you reduce the amplitude of your drive, so compare
Yeah.
relatively second harmonic and third harmonic.
I don't know. I didn't do this. The way it looks, just from my memory, I think it looks pretty much the same. It was much weaker than the first harmonic, just because the non-linearity kind of is small.
Is this an intermediate strength effect?
Qualitatively, I can't really answer.
So shouldn't this be intermediate strength? If I drive it even harder, so that there's no sense in which perturbation theory even is good, the third harmonic generation dominating the first harmonic.
There might be something like that.
Right.
You can also you could drive it at a third of the resonance frequency. Try to see if you can trigger.
Or I'm just talking about as far as amplitude. You drive with the same thing, but you just increase the amplitude so much that the third harmonic at perturbation level dominates the first harmonic.
Yeah, I have to admit I didn't study what happens if I drive. Yeah, so no, I did actually. Just didn't think about it in such a way. So I looked what happens if you drive it even stronger. And the thing is that the resonance condition slips away because you have this blue shift that shifts your resonance frequency into the range where you actually have the resonance, namely it lies the driving frequency. But when you drive even stronger, the resonance again shifts away, and then you are getting out of this instability. But that is not saying that if you go far here, you will not hit something else. Could be. I think this paper by Olsen and Olsen, they say something like this because they are studying in the end chaos.
Mm-hmm.
So I think they're saying something about that.
Then a curiosity question. Can you explain the framework of you have a photon and a phonon coupled
As a hybrid.
in entangled.
Could be interesting, but I don't know what to expect. Maybe it goes a little bit in the direction of what you asked. If you have, say, cavity where these mode hybridize, could be interesting, but I don't know what happens. Have to think about it.
But in that case, your intensity is so strong, I think it goes into the classical region. So entanglement is very hard to.
Yeah, maybe I will think about something like that when I think about optomechanics, because this is in quantum regime.
Well, I guess that's all the time we have for today. So let's thank the speaker again.